And now in this lecture we'll answer two questions. In the first question we find out the area of this big circle, and in the second question we find out the area of this rectangle ABCD in two different methods. So we'll start with the first question. In the drawing we have two circles that touch each other at point C. Point C is the point of tendency of those two circles with each other. We know that this is line segment BC, that is equal to 9 units in its length. This is line segment CA, that is equal to 16 units in its length. In addition, we know that this is tangent DE, that is tangent to this small circle at this point, point B. And tangent DE also tangent to the big circle at this point. So we define the point of tendency of tangent DE with this big circle at this point as point M. And we focus on this point, point B. Point B is considered as an external point in relation to this big circle. So from this common external point, point B, we have tangent BM that is tangent to this big circle at point M, and from the same common external point, point B, we have this chord CA. If we draw this straight line CB and extend it, it will cut the big circle at 2 points, point C and point A. In this way we create chord CA. So here we can implement rule 10. Repeat quickly on rule 10. According to rule 10 is true in any circle. In any circle, if AB is any chord in the circle, here AB is a chord of this circle, and PT is a tangent to the circle. PT is tangent to this circle at point T. Then in this drawing, the following equation is true: that PT square equals to PA times PB. Again, PT square equals to PA times PB. So whenever you draw from a common external point a tangent to a circle, and it's also from the same common external point you will draw a straight line that cuts the circle at 2 points, and in this way you will create a chord. Then the following equation will be true: that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can actually implement rule 10 in our drawing. In our drawing, from this common external point, point B, we have tangent BM, and from the same common external point, point B, if we draw this straight line, it will cut the big circle at 2 points C and A. In this way, we created chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement a rule 10. According to rule 10, the following equation will be true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I write it down. BM square equals to BC times BA. repeat again, according to rule 10, if you focus on the common external point B, the following equation will be true that BM squared equals to BC times BA. BM is the missing tangent, so we'll write as it is. BM squared equals to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So I shall found out that according to rule 10, BM squared equals to 9 times 25. Here we take a water out of this equation and we get that BM, tangent BM, the graph of tangent BM is square root of 9, that is 3, times square root of 25, that is 5. So in total BM equals to 3 times 5, that is 15. So the length of tangent BM is 15 units. In the next step, we will do a construction. That is to say, from point C, we will draw two tangents. We draw a common tangent. The tangent will be tangent to both circles, to the small circle, and it will be also tangent to the big circle at point C. Okay. Point C is also the touching point of the two circles. And we will define the touching point of the common tangent C with tangent DE, this point is point N. Repeat again, tangent CN is a common tangent that belongs to both circles. Tangent CN is a tangent to the small circle at point C, and tangent CN is also tangent to the big circle at the same point, point C. In the next step, we'll focus on this common external point, point N. From this common external point, point N, we have two tangents to the small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. So I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Here, as I already mentioned, from the common external point, point N, we have two tangents to the small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. In the next step, we join point C and M together by side line. So I'll copy the right triangle. It is not a right triangle. I'll copy triangle C and B in a new page, and we'll analyze this triangle C and B. So actually this is triangle this is triangle C and B that are going on your drawing. And this triangle C and B, side CN equals to side NB, according to rule 2. And we have also the rule that states that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle, and in front of this side NB we have this angle. And those two angles, because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other in their sizes. So if we define the size of this angle NCB as alpha, then the size of this angle CBN must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So if we found out that angle NCB equals to alpha, this is angle NCB that is equal to alpha, and angle CBN also equals to alpha. This is angle CBN that is equal to alpha. We continue to focus on this convex point N. For this convex point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. NC equals to NM. So in the next step, I'll copy the right triangle CNM in the new page, and we will analyze this triangle CNM. So actually, this is triangle CMN that I correct from the original drawing. In this triangle CMN, side CN equals to side MN according to rule 2. And according to the same rule that I mentioned, 2 minutes ago, the rule says that in front of equal sides in the triangle there are equal angles. In front of this side CN, we have this angle CMN, and in front of this side NM, we have this angle, that is actually angle NCM. And because of the fact that those two angles are both located in front of those two equal sides, they must be also equal to each other in their sizes, according to the rule that I mentioned. So if we define the side of this angle NCM as beta, then the side of this angle CMN must be also equal to beta, because they are equal to each other according to the rule that I mentioned. In conclusion, if we found out that angle MCN equals to beta, this is angle MCN that is equal to beta, and angle NMC also equals to beta. This is angle NMC that is also equals to beta. In the next step, I'll copy the big triangle MCN, MCB. Triangle MCB consists of the two triangles MCN and NCB. So I'll copy the big triangle MCB in the new page and analyze this triangle, triangle MCB. So here, this is triangle CMB that I go from the original drawing. In this triangle CMB, the sum of the angles must be equal to 180 degrees. This is true in any triangle, and this is of course true in this triangle, triangle CMB. So which angles we have in triangle CMB? We have angle alpha plus angle beta plus this big angle that is alpha plus beta, or beta plus alpha. In total, they must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation we have alpha plus alpha is 2 alpha, plus beta is 2 beta. In total, the sum of those two angles must be equal to 180 degrees. Here we divide this equation by 2, and finally we get that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So if we found out that this big angle MCB that is equal to alpha plus beta, it is a right angle. So this is the big angle MCB that is equal to alpha plus beta, and alpha plus beta is 90 degrees, so angle MCB is a right angle. It is given as the question that AB is a straight line. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. And therefore, this missing angle must be equal to 90 degrees in its size. So if I found out that angle ACM is a right angle. In the next step, we'll join points A and M together by a straight line. AM is a chord inside the big circle. Again, AM, line segment AM is a chord in the big circle. So here we have peripheral angle ACM. This is peripheral angle ACM, and we just right now found out that according to rule 3, peripheral angle ACM is a right angle. Peripheral angle ACM equals to 90 degrees in its size. So here we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle MAN, and we know that peripheral angle MAN is a right angle. This is to say it is equal to 90 degrees in its size. And according to this rule 5, whenever you have a peripheral angle that is a right angle that is equal to 90 degrees in size, then it must subtend on the diameter of the circle. It is very easy to see that peripheral angle MAN subtend on MN, and therefore MN must be the diameter of the circle, according to this rule 5. So whenever you have a peripheral angle that is equal to 90 degrees in its size, then that peripheral angle must subtend on the diameter of the circle. We can definitely implement rule 5 in our drawing. Why? Because in our drawing so as I mentioned, peripheral angle ACM is a right angle, and according to rule 5, any peripheral angle that is a right angle must subtend on the diameter of the circle. Peripheral angle ACM that is a right angle subtend on AM, and therefore AM must be the diameter of the circle, of the big circle, according to rule 5. So I write it down. So chord AM is the diameter of the big circle, this big circle, according to rule 5. So I write it down. Chord AM is the diameter of the big circle according to rule 5. We also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. So AM is the diameter of the big circle, and therefore the center of this big circle must be located on AM. So here we will define this point O, and point O is the diameter of this big circle. Point O is the center of this big circle. you can see that point O is indeed located on AM, that is the diameter of this big circle. So point O is the center of this big circle. Point M is the point on the big circle itself. Therefore, OM is the radius of this big circle. We'll define the radius OM of this big circle as R. So OM equals to R. This is the radius of the big circle. And because of the fact that the radius OM, that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, I'll copy the right big triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right big triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side, the diameter AM is unknown, we don't know what is the length of the diameter AM. Side M equals to 15 units in its length according to rule 10. And the hypotenuse AB in total equals to 9 plus 16, that is 25. Again, the hypotenuse AB is equal to 25 units in its length. Here by PT is the proportion from Pythagoras theorem. So actually, this is the right big triangle A and B that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625. And it is equal to AM squared. AM is the missing side, so we leave it as it is, so it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total we found out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400. So 400 equals to AM squared. So here we take a root out of this equation, and finally get that AM, the missing side AM, is equal to the square root of 400, that is 20. AM equals to 20 units in its length. AM, you know the chord AM is the diameter of the big circle. So, if the diameter of the big circle equals to 20 units in its length, it means that the radius must be equal to half of it. So the radius R of the big circle must be equal to the length of the diameter AM over 2. AM is 20, so in total the radius of the big circle must be equal to 20 over 2, that is 10. So in total we found out that the radius R of the big circle is equal to 10 units in its length. Our mission is to find out the area of this big circle. Actually, the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, and therefore the radius of the area of the big circle must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159 square units. Repeat again, I shall find out that the area that we are looking for in this question, that is the area of this big circle, it is equal to either 100 pi square units, so in terms of numbers, the area of this big circle is equal to 314.159 square units. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. I'll repeat again that we will find the area of this rectangle ABCD in two different methods. So we'll start with the first method. So in the drawing we have rectangle ABCD, and we have also this semicircle. In addition, we have here 9 cm AM, that is equal to 5 units in its length. Repeat again, our mission is to find out the area of this rectangle ABCD. First of all, we know that because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle ABCD are right angles. So, okay, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. So point O is the center of this semicircle, point A is the point of the semicircle itself, therefore always the radius of this semicircle that is equal to x units in its length according to our definition. In the next step, we'll define the point of tendency of tangent DC with this semicircle. This point is point E. And we'll join points O and E together by a straight line. What is the definition of line segment OE? line segment OE starts from point O, that is the center of the semicircle, and ends at point E, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle that is equal to x units in its length according to our definition. OE equals to x is the radius of the semicircle. And because of the fact that the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in quadrilateral OADE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle and not a square. So we relate to quadrilateral DEOA as a rectangle because it has 4 right angles. Quadrilateral DEOA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But DEO is x, it is the radius of the semicircle, that is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A, and we define this line segment MB as B. In the next step, we join points O and M together by a straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of the semicircle, and ends at point M, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle that is equal to x units in its length according to our definition. In the next step, I'll copy the right triangle OMB in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle OMB. Here by PT is a version for Pythagoras theorem. The hypotenuse OM equals to x units in its length. It is actually also the radius of the semicircle. So this is triangle OMB that I copied from the original drawing. In this triangle OMB, according to the Pythagoras theorem, MO squared, that is the square of the hypotenuse, equals to MB squared plus BO squared. Repeat again, MO squared equals to MB squared plus BO squared. So I write it down. This will be equation 1. So MO squared, that is the square of the hypotenuse, equals to MB squared plus OB squared. The hypotenuse MO is x, therefore MO squared is x squared. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus BO squared. BO is A, therefore BO squared is A squared. So in total we found out that according to equation 1, x squared equals to B squared plus A squared. In the next step, we'll copy the right triangle, the right big triangle, triangle A and B in the new page, and we'll implement the Pythagoras theorem on this right triangle, triangle A and B. It is very easy to see that AB in total equals to x plus A, and B equals to B, and the hypotenuse MA equals to 5 units in its length, according to what is given as the question. This is triangle A and B, it is the equation from the original drawing. Here by PT is the equation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle A and B, MA squared, that is the square of the hypotenuse, equals to MB squared plus BA squared. So I write it down. This will be equation 2. So MA squared, that is the square of the hypotenuse, is equal to MB squared plus BA squared. MA is 5, therefore MA squared is 5 squared, that is 25. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus BA squared. BA is x plus A, therefore BA squared is x plus A squared. So in total, according to equation 2, we actually found out that (25) equals to B squared plus A, B squared plus x plus A squared. So 25 equals to b squared plus x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times x times a. So in the right side of equation 2, we have the expression b squared plus a squared. But we have already found out that according to equation 1, b squared plus a squared equals to x squared. Therefore, we substitute b squared plus a squared in equation 2 by x squared from equation 1. For this equation 1. We do it now, we get that according to equation 2, 25 equals to, again, b squared plus a squared is x squared according to equation 1. We have x squared again, plus x squared, plus 2xa. So in total we found out that 25 equals to x squared plus x squared is 2x squared, plus 2xa. Here we divide this equation 2 by 2, and finally get that 25 over 2 is 12.5, and it is equal to 2x squared over 2 is x squared, plus 2xa over 2 is xa. So according to equation 2, we found out that 12.5 equals to x squared plus xa. Here we take x, we take out x as a common factor of those two expressions. So x was taken out as a common factor from those two expressions. So what is left from x squared after we took from it x as a common factor? What is left is actually x. And also xa. What is left from xa after we took from it x as a common factor? What is left is actually a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Again, 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. It is true in any rectangle, especially it is true in rectangle ABCD. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle. The area of rectangle ABCD must be equal to the length of rectangle ABCD times the width. The length of rectangle ABCD is AB. The length is AB times the width. The width is DA. So in total, we shall find out that the area of rectangle ABCD must be equal to AB times DA. AB is x plus a times DA. DA is x. So in total, we found out that the area of rectangle ABCD equals to x plus a times x. But according to equation 2, according to this equation 2, x plus a times x equals to 12.5. Therefore, we can substitute x plus a times x here by 12.5. We'll do it now, we'll get that the area of rectangle ABCD equals to 12.5 square units. And that is the answer to the question. Repeat again, we found out that the area that we are looking for in this question, this is the area of this rectangle ABCD. The area of this rectangle ABCD is equal to 12.5 square units. So if we finish with the first method, in the next step I will present to you how to find out the area of this rectangle ABCD in the second method. because of the fact that ABCD is a rectangle, all those four angles inside of the ABCD are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. And we define the radius of this semicircle, x, exactly as x, exactly as we did in the first method. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that is equal to x units in its length according to our definition. We have already found out in the first method that side DA is equal to x. So I will not repeat on the same explanation. So side DA is equal to x units according to the first method. In the next step, we define the length of this line segment OB as A, and we define this point as N. In the next step, we join points N and M together by a straight line. By joining points M and N together by a straight line, we can do peripheral angle AMN. This is peripheral angle AMN, and because of the fact that this peripheral angle AMN subtends on AN, that is the diameter of the semicircle, therefore, according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. And therefore, this peripheral angle AMN must be equal to 90 degrees. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. Okay, so here we have the drawing a circle, and we know that AB is the diameter of the circle. Again, we know that AB is the diameter of the circle, and this is peripheral angle ACB. We don't know what is the size of peripheral angle ACB, but because of the fact that this peripheral angle ACB subtends on AB, that is the diameter of this circle, it must be equal to 90 degrees in its size. So peripheral angle ACB equals to 90 degrees in its size according to this rule, rule 7. Any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size according to this rule, rule 7. As I already mentioned before, you can definitely implement rule 7 in our drawing. Because of the fact that this is peripheral angle MAN that subtends on AN, that is the diameter of this semicircle, therefore it must be equal to 90 degrees in its size. So this is peripheral angle MAN. That is the right angle according to rule 7. In the next step, we define this angle as alpha, and we focus on the right triangle AMN. Inside this right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on the right triangle A and B. This is the right triangle A and B. In this right triangle A and B, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the triangle AMN, and this angle A also belongs to the right triangle AMB. And therefore, angle A is a common angle that belongs to both triangles. Okay, so in the next step, I'll copy the right triangle AMN and the right triangle AMB in a new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. Repeat again that this is angle A, that is a common angle that belongs to both triangles. It belongs to the right triangle AMB, and it also belongs to the right triangle AMN. So actually, those are the two right triangles, triangle A and B and triangle AMN, that are copied from the original drawing. This angle equals to 90 degrees minus alpha. And again, those are the two right triangles, A and B and AMN, that are copied from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So okay, this is angle ABM. In the right triangle AMB, and it is equal to this angle that is actually angle AMN. In the right triangle, triangle AMN. They are both equal to 90 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle AMB. In the right triangle AMB, and it is equal to this angle, that's actually angle ANM. In the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, as I already mentioned before, this is angle A. We have also the same angle here. So angle A is a common angle that belongs to both triangles. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle A, as it belongs to the right triangle A and B, it will be defined as angle BAM. And angle A equals to itself. So if we relate to angle A, since it belongs to the right triangle AMN, it will be defined as angle MAN. This equation means that angle A equals to itself. We just put to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. So we proved that all the triangles of this right triangle A and B are correspondingly equal to all the triangles of this right triangle AMN, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that triangle AMB is similar, this is the sign of similar to the right triangle AMN, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive, but before that, we know that it is given as the equation that line segment AM equals to 5 units in its length. AM equals to 5 according to what is given as the equation. AN is the diameter of the semicircle. The radius of this semicircle is x. Therefore, the diameter must be twice as long as the radius. The radius is x, therefore the diameter must be equal to 2x. Therefore, AN equals to 2x units in its length. AN is the diameter that is equal to 2x units in its length. AB in total equals to x plus A. So from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. So repeat again. We will derive that side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM is 5 over AN. AN is 2x, and it is equal to AB, that is x plus A, over AM, that is 5. So in total, if we found out that 5 over 2x equals to x plus A over 5. Here we cross multiply this equation, equation 1. And you get that according to this equation, equation 1, 5 times 5 is 25. And it is equal to 2x times x plus A. Here we divide this equation, equation 1 by 2. And finally you get that 25 over 2 is 12.5. And it is equal to 2x over 2 is x. So in total this expression equals to x times x plus A. So according to equation 1, we have found out that 12.5 equals to x times x plus A. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Repeat again. The area of any rectangle equals to the length of the rectangle times the width of the rectangle. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB times the width. The width is DA. So in total, we found out that the area of rectangle ABCD equals to AB times DA. AB is x plus A, and DA is x. So in total, we found out that the area of rectangle ABCD equals to x plus A times x. But according to equation 1, this equation 1, x plus A times x is 12.5. So we substitute x plus A times x here by 12.5. So in total, we found out that the area of rectangle ABCD equals to 12.5 square units. Repeat again. In both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. So, in the next step, let's summarize the lecture. We'll start with the first question, of course. In this first question, our mission is to find out the area of this big circle. So, in the drawing, we have two circles that are tangent to each other at this point C. Or, in other words, they touch each other externally at point C. Okay? In addition, you know that this is line 7CB, that is equal to 9 units in itself. This is line 7AC, that is equal to 16 units in itself. This is this is a tangent DE, that is tangent to this small circle at point B, and tangent DE is tangent to this circle at this point. So we find the point of tendency of tangent DE with this big circle as point M. And we focused on this common sub point B. From this common sub point B, we have tangent BM, and from the same common sub point B, if we draw this straight line, it will cut the big circle at 2 points, point C and point A. In this way, we get here called AC. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. Okay, again, actually, if we focus on the common sub point B, according to rule 10, the following equation is true: that BM square equals to BC times BA. BM is the missing side, so we leave it as it is. BC is 9, BA in total is 9 plus 16, that is 25. So we found out that BM square equals to 9 times 25, because BA is 25. Here we took a root out of this equation, and found out that BM equals to the square root of 9, that is 3, times square root of 25, that is 5. So in total BM equals to 3 times 5, that is 15. And again, we found out that the length of this standard BM is 15 units. In the next step, we did a construction. That is to say, we draw a tangent that is tangent to both circles at point C. Again, we draw a tangent that is tangent to both circles at point C. That is to say, we draw a common tangent that is tangent to both circles. And we define the touching point of the common tangent with tangent DE. This point is point A. Okay, again, tangent AC is a common tangent, that is to say, tangent NC is a tangent to the small circle at point C, and tangent NC is also tangent to the big circle at the same point, point C. In the next step, focus on this common sub point N. From this common sub point N, we have two tangents to the small circle, tangent NB and tangent NC, and according to rule 2, they are equal to each other. That is to say, NB equals to NC. In the next step, we copy triangle NCB in the Olympiad and analyze this triangle NCB. So here, this is triangle NCB that I copied from the original drawing. Side CN equals to side NB according to rule 2. And according to the rule that states that in front of equal sides in the triangle there are equal angles, we get that in front of this side CN we have this angle. In front of this side NB we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be equal to alpha, because they must be equal to each other according to the rule that I mentioned. So in total, we found out that angle NCB equals to alpha, and angle CBN also equals to alpha. In the next step, we join point C and M together by straight line, and we continue to focus on this common sub point N. From this common sub point N, we have two tangents to the big circle, tangent NC and tangent NM, and according to rule 2, they are equal to each other. That is to say, NC equals to NM. In the next step, I copied triangle C and M in your page, and we analyze this triangle C and M. This is triangle C and M that I copied from the original drawing. According to rule 2, side NM equals to side NC. And according to the sum rule that I already mentioned, the rule states that in front of equal sides in the triangle there are equal angles. in front of this side NA we have this angle, in front of this side NC we have this angle. And because of the fact that those two angles are located in front of those two equal sides, it must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. So in total we found out that this is angle NCM, that is beta, and angle NMC is also beta. In the next step I copied the big triangle MCB. The big triangle consists of those two small triangles that we talked about them. So I copied the big triangle MCB in the new page. Analyze this big triangle, triangle MCB. Okay, this is triangle MCB that I copied from the original drawing. We have the rule that says that the sum of the angles in any triangle is equal to 180 degrees. This rule is true in any triangle, and especially it is true in this triangle, triangle MCB. So which angles we have in triangle MCB? We have this is angle alpha plus this is angle beta plus this is angle beta plus alpha. In total, the sum of those two angles must be equal to 180 degrees. In this side of the equation we have alpha plus alpha, this is 2 alpha. Beta plus beta is 2 beta, so in total we have 2 alpha plus 2 beta equals to 180 degrees. We divide this equation by 2 and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. That is to say, this is angle MCB is equal to alpha plus beta. So angle MCB is a right angle according to this equation. So actually, this is angle MCB, that is a right angle. Okay, it is given as a question that AB is a straight line. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees, according to the rule that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, here we have peripheral angle ACM, that is a right angle according to rule 3. Peripheral angle ACM is a right angle. So, according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. It is very easy to see that peripheral angle ACM subtends on AM. Therefore, according to rule 5, peripheral angle ACM, that is a right angle, and subtends on AM. Therefore, according to rule 5, AM must be the diameter of this big circle. Again, according to rule 5, if we relate to the big circle, chord AM is the diameter of the circle according to rule 5. We know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. And therefore, the center of this circle must be located on the diameter AM. So, this is point O that we defined as the center of this big circle. Point O is definitely located on AM, that is the diameter of the circle. So point O is the center of this big circle, point M is the point on the big circle itself. Therefore OM is the radius of this big circle. We define the radius of this big circle as R, so OM equals to R. Because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. In the next step, I copied the right big triangle, triangle A and B in a new page, and implemented the Pythagoras theorem in this right triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares from the perpendiculars. So actually, this is the right triangle A and B that are covered from the original drawing. Side AB equals to 15 units according to rule 10. AB in total equals to 16 plus 9, that is 25. Therefore, AB equals to 25. AM is the missing side. According to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. AB squared equals to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we leave it as it is, plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, I found out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation. 625 minus 225 is 400, so 400 equals to AM squared. Here we took a root out of this equation and found out that the missing side AM equals to the square root of 400, that is 20. AM equals to 20 units in its length. AM is the diameter of the big circle. If the diameter AM equals to 20 units, it means that the radius must be equal to half of it. That is to say, the radius must be equal to 20 over 2, that is 10. So if I found out that the radius of this big circle equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of the big circle must be equal to pi times the radius of the big circle squared. But the radius of the big circle is 10. And therefore, the radius squared is 10 squared. 10 squared is 100. So in total, this expression equals to 100 pi. So if you found out that the area that we are looking for in this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. We finished with the first question. In the next step, I presented to you the second question, and we solved the second question in two different methods. Our mission in the second question is to find out the area of this rectangle ABCD. So we start with the first method. In the drawing we have rectangle ABCD, and we have also this semicircle. In addition, we have here line segment AM, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD must be right angles. And we defined the radius of this semicircle as O, and we defined the center of this semicircle as O, and we defined the radius of this semicircle as X. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to X units in its length, according to our definition. In the next step, we define the point of tendency of tangent DC with this semicircle. This point is point E. In the next step, we join points O and E together by a straight line. What is the definition of line segment OE? Line segment OE starts from point O, that is the center of the semicircle, and then to point E, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle, that is equal to X units in its length according to our definition. Because of the fact that the radius OE of this semicircle that is equal to X, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do the quadrilateral DEOA. Inside this quadrilateral DEOA, we have 1, 2, 3 triangles. The sum of three right angles is 270 degrees, so 270 degrees plus the size of this opposite angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this opposite angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA we have four right angles. According to rule 5, any quadrilateral that has four right angles must be at its right angle plus a square. So we relate to quadrilateral DEOA as right angle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle DOA, sine EO must be equal to the opposite side DA. But EO is the radius of this semicircle that is x, therefore DA must be also equal to x units in its length. Okay. In the next step, we define this line segment OB as A, and we define this line segment AB as B. We have already found out that OA is the radius of this semicircle that is x. In the next step, I copied the right triangle MBO on the new page and implemented the Pythagoras theorem on this right triangle MBO. This is the right triangle MBO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle MBO, MO squared equals to MB squared plus BO squared. MO is x, therefore MO squared is x squared. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus BO squared. BO is A, therefore BO squared is A squared. So in total, according to equation 1, we should find out that x squared equals to B squared plus A squared. In the next step, I copied the right big triangle A and B in the new page and we implemented the Pythagoras theorem and this right triangle A and B. The hypotenuse AM equals to 5 units in its length according to what is given as the question. Side AB equals to B and side BA in total equals to x plus A. So actually this is the right triangle A and B that are coming from the original drawing according to the Pythagoras theorem. In this right triangle A and B, AM squared, that is the square of the hypotenuse, equals to MB squared plus BA squared. AM is 5, therefore AM squared is 5 squared, that is 25, and it is equal to MB squared. MB is B, therefore MB squared is B squared plus BA squared. BA is x plus A, therefore BA squared is x plus A squared. So in total, according to equation 2, we should find out that 25 equals to B squared plus x plus A squared. So 25 equals to B squared plus x plus A squared. X plus A squared equals to x squared plus A squared plus 2 times x times A. In this side of equation, this equation 2, we have the expression B squared plus A squared. But according to equation 1, we have only found out that B squared plus A squared equals to x squared. Therefore, we can substitute B squared plus A squared in this equation 2 by x squared from equation 1. We did it, and we should found out that according to equation 2, 25 equals to B squared plus A squared is x squared. We have x squared again, plus 2xa. So in total, we should find out that 25 equals to x squared plus x squared is 2x squared plus 2xa. So in total, we should find out that according to equation 2, 25 equals to 2x squared plus 2xa. Here we divided this equation 2 by 2, and finally found out that 25 over 2 is 12.5, and it is equal to 2x squared over 2 is x squared plus 2xa over 2 is xa. So in total, according to equation 2, we actually found out that 12.5 equals to x squared plus xa. So 12.5 equals to, here we have x squared plus xa. So we took out s as a common factor of those, out of those two expressions. So what is left from x squared after we took from it x as a common factor? What is left is actually x, and what is left from xa after we took from it x as a common factor? What is left is actually a. So in total, according to equation 2, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Again, our mission is to find out the area of rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width of the rectangle. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB is x plus A, DA is x. So in total, the area of rectangle ABCD must be equal to x plus A times x. but x plus a times x, according to equation 2, x plus a times x is 12.5. Therefore, we can substitute x plus a times x here by 12.5. We did it, and we should have found out that the area of rectangle ABCD equals to 12.5 square units. The area of this rectangle ABCD equals to 12.5 units in its length. And this is equal to 12.5 square units in its size. So we finish with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. We know that ABCD is a rectangle, therefore all those triangles inside rectangle ABCD are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x, exactly as we did in the first method. We already found out in the first method that dA equals to x, so I'll not repeat on the same explanation. And we defined this line segment OB as A. We define this point as N. The next step, we join points M and N together by a straight line. By joining points M and N, we created peripheral angle MNA. This is peripheral angle MNA. It is very easy to see from the drawing that peripheral angle MNA subtends on AN, that is the diameter of the semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. Therefore, peripheral angle NMA must be equal to 90 degrees according to rule 7. In the next step, we define this angle as angle alpha. So in the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. Likewise, focus on the right angle A and B. In this right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Okay? According to the same explanation, this angle equals to 90 degrees minus alpha. In the next step, I copy the right angle AMN and this right angle AMB. And in the question, we prove that those two right angles are similar to each other according to angle similarity rule. Okay, those are the two right angles A and B and the AMN that are going from the original drawing. AB equals to x plus A. AM equals to 5 units in its length according to what is given as the question. AN is the diameter of the semicircle. If the radius of the semicircle is x, the diameter must be equal to twice. The diameter must be twice as long as the radius. If the radius is x, then the diameter must be equal to 2x. So AN equals to 2x. AN equals to 2x. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. This is angle A, that is a common angle that belongs to both angles. It is very easy to see that angle A belongs to the right angle AMN, and angle A also belongs to the triangle AMB. So, in addition, angle A is a common angle that belongs to both angles, so we can write down that angle A equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the figures of the right angle A and B correspond equal to all the figures of this right angle A and M, and therefore those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive the side AM of the right angle A and B over side AN of the right angle AMN equals to side AB of the right angle AMB over side AM of the right angle AMN. Okay, I'll repeat again. We will derive the side AM of the right angle AMB over side AN of the right angle AMN equals to side AB of the rectangle AMB outside the n of the rectangle outside the m of the rectangle AMN. AM is 5, AN is 2x, AB is x plus a, and AM is 5. So in total, according to equation 1, 5 over 2x equals to x plus a over 5. Here, of course, multiply this equation 1, and finally found out that according to this equation 1, 5 times 5 is 25, so 25 equals to 2x times x plus a. Here we divided this equation 1 by 2, and finally found out that 25 over 2 is 12.5, and this is equal to 2x over x is x. So in total, this expression equals to x times x plus a. So according to equation 1, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width of the rectangle ABCD. The length of the rectangle ABCD is AB. The width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB in total is x plus a, DA is x. Okay, again, AB is x plus a and DA is x. So in total, the area of rectangle ABCD must be equal to x plus a times x. But according to equation 1, this equation 1, x plus a times x is 12.5. Therefore, we can substitute x plus a times x here by 12.5. We did it, and we found out that the area of rectangle ABCD equals to 12.5 square units. So in both methods, we found out that the area that we are looking for in this question, that is the area of this rectangle ABCD, is equal to 12.5 square units. Okay, thank you very much.